Besides VOR and ADF, there are various types of advanced navigation systems and indicators available. Our purpose in this section is to introduce you to some of them and describe their capabilities. The first system we'll look at is area navigation based on signals transmitted by VORTAC, or VOR DME stations. As you learned earlier, VOR provides for navigation between stations. But VORTAC-based area navigation allows you to fly directly to your destination, often with considerable savings in time and operating costs. To accomplish this, a CourseLine computer allows you to electronically relocate or offset navigation aids to a desired radial and distance from the original location. These offset stations are called waypoints. For example, assume you're planning a direct flight from Storm Lake Municipal Airport to Algona Municipal Airport, and you're using area navigation equipment. The first thing you must do after determining your route is to select the closest VORs to your flight path. In this case, they are the Spencer and Fort Dodge nav aids. Then establish waypoints along the route and determine the radial and distance each waypoint is from the VOR. Waypoint number 1 is 27 nautical miles from Spencer on the 140-degree radial. Waypoint number 2 is on the 335-degree radial, 23 miles from Fort Dodge. These values are then entered into the receiver prior to your departure. Now you can simply fly from waypoint to waypoint until you reach your destination. Your course information is displayed on the VOR indicator just as it is in normal VOR navigation. If you drift off course, the CDI points toward the desired course. However, the deviation is indicated in nautical miles instead of degrees. The mileage that each dot represents is determined by the manufacturer. Now let's look at another form of area navigation called long-range navigation, or LORAN. This system also lets you fly directly to your destination, but with LORAN, you don't have to create waypoints. Instead, it uses a network or chain of stations which transmit low-frequency signals in the 90 to 110 kilohertz range. These low-frequency signals follow the contour of the Earth in the form of a ground wave and have a reliable reception range of 600 to 1,200 nautical miles. LORAN transmitters can also produce sky waves which increase the reception range, but these signals are not considered reliable for navigation. In a typical LORAN chain, there is a master station and 2 to 5 secondary or slave stations. The master station first transmits a coded pulse group. Then, each secondary station transmits its pulse at a specific time interval after the master pulse. A LORAN receiver in the aircraft determines your position by measuring the time difference between the receipt of the master pulse and that of the secondary stations. Your position is then translated into latitude and longitude values and displayed on the receiver. After you enter the destination, the receiver displays course and distance to the specified point. During the flight, it provides a continuous update of the information. Because LORAN operates in the lower frequency range, electrical disturbances such as lightning and precipitation static can cause signal loss or distortion. For this reason, aircraft with LORAN units should have static discharge wicks and bonding cables to help dissipate any static buildup. Another limitation is the variation in speed at which the radio signals travel. The surface type, foliage, and seasonal changes can affect the speed of the radio waves and decrease their accuracy. There are several types of LORAN units available, and their capabilities vary considerably. Besides bearing and distance, some receivers provide wind direction and velocity, fuel consumption, and other types of information. You can determine the features and limitations of the particular unit you're using by referring to the owner's manual or to placards located on the instrument panel. Another type of navigation that is quickly replacing traditional ground-based navigation systems is the Global Positioning System, or GPS. This type of navigation system relies on signals received from satellites to calculate the position of the aircraft. A GPS receiver determines an aircraft's position through triangulation of distance measurements from a minimum of 3 satellites. And because this system is satellite-based, it doesn't have the limitations that a ground-based system might have. It provides the same benefits as other point-to-point navigation systems, but with unmatched accuracy. 95% of the time, lateral position accuracy is within 100 meters of the true horizontal position. GPS receivers incorporate a wide array of navigation capabilities that help increase situational awareness, such as moving map displays and the ability to select the nearest airport. With such a wide variety of manufacturers and options comes the responsibility to understand the operation and limitations of the system you use. Your pre-flight preparation should include a review of GPS and how your particular system functions. GPS units come in both panel-mounted and handheld units. Handheld units are meant only for flight under VFR conditions and are not certified for use under IFR conditions. Each GPS unit has a different type and location of the receiver antenna. Panel-mounted GPS units have permanently affixed antennas. A handheld unit, however, may have a self-contained antenna or a detachable antenna. You need to make sure these antennas are in a location that provides adequate signal reception. It is also your responsibility to verify that a panel-mounted unit has been properly installed and maintained in accordance with the AFM or POH. You should also be aware that GPS systems utilize Receiver Autonomous Integrity Monitoring, or RAIM. RAIM checks the integrity of the navigation solution and alerts the GPS user to a position error. Many handheld GPS receivers do not have RAIM alerting capabilities. These receivers should not be used as the sole system of navigation. Instead, you should integrate GPS with other forms of navigation such as VOR, pilotage, or dead reckoning to ensure navigation accuracy. Most GPS units include a navigation database. Flying with an outdated database is like using an expired sectional chart. In fact, to fly IFR by GPS, you must have a current, updatable database. Since both airspace and navigation data are constantly changing, you should apply this requirement to VFR GPS use as well. GPS is rapidly becoming the standard means of navigation. Take the time to become familiar with the unit you will use, planning your flights carefully prior to departure, and when possible, programming your GPS on the ground. In addition, always check NOTAMs for any outages in the GPS system that would affect GPS navigation. Another way to increase your navigation capabilities is through use of specialized instruments. One such instrument is the Horizontal Situation Indicator, or HSI. It combines the functions of 2 instruments in one display. Its movable compass card works like a heading indicator to give you magnetic heading information. The other elements work like a VOR indicator to help you maintain your orientation to the station. Let's take a look at the components to help you understand the capabilities of HSI. A heading select bug is an index that rotates when you turn the heading select knob. If an autopilot is engaged, the airplane will automatically turn to the heading you select with the bug. If an autopilot is not used, the select bug serves only as a reference marker as you complete the turn. Like the CDI, the lateral deviation indicator tells you if you are left or right of course. When you are on course, the needle is aligned with the course arrow and the reciprocal course pointer. The ambiguity indicator works like a to/from indicator to tell you if you are flying to the VOR or from it. One other feature that HSI provides is glide slope information, which is used during instrument approaches. You may learn more about this if you proceed with additional pilot training. Now let's look at another advanced instrument, the radiomagnetic indicator, or RMI. The RMI combines the functions of 3 instruments: the heading indicator, the VOR indicator, and the ADF indicator. The slaved compass card automatically displays your magnetic heading at the top index. Typically, the single needle indicates the magnetic bearing to the VOR station, while the double needle shows the bearing to the NDB. The tail of each needle indicates magnetic bearing from the station. With the needles indicating the bearings to separate navigation aids, constant position orientation is provided. You can track toward one facility while monitoring your progress on another. The information presented in this section is intended to serve only as an introduction to advanced navigation. Be sure to refer to the operating handbook for details on the system you are using.